Good afternoon. I am Anil Kumar, and in the EduSet course, I am taking lecture on image classification techniques. In this lecture, you will found that the different topics I am covering. One is separability analysis, the second is image classification, and third is accuracy assessment. So today we'll try to start with separability analysis topic, and then we'll go for image classification. The first, this separability analysis. If you think about a multispectral image, there can be 4 to 10 or 12 spectral bands, and if you talk about hyperspectral image, you may have large number of 100 200 contiguous bands. So when the bands are more, and if you are extracting, suppose C is equal to number of classes, suppose 6 you are extracting from a given image, and if your processing machine is not very high and it may take a lot of time if the image size is also very big. So to cut down the time and find out the optimum spectral bands which can give maximum separation between the classes we are trying to map. So for this, the answer we can get through separability analysis. And before that, we can just highlight what is image. You can see this rows also looks to be an image to be defined. This also looks to be an image. This also to be looks to be an image, and this also to be looks an image. But if you try to define the image with a book definition called pictorial representation, so it is not understood to a person who is going for digital image processing. So for that we have to see further definition of what is image. And here for the satellite also, if you zoom some portion, this is a satellite image, and if you try to zoom up to certain level, you see the pixels which are appearing like a small boxes. And further, if you zoom within this box, you will find some numbers, and these are your digital numbers. Image is basically actual. When you're looking to process the image, you should understand the definition of image is the numbers which are arranged in the form of rows and column, and you may have multiple layers. It can be single layer if it is panchromatic image. If it is multispectral image, you may have 2 or more than 2 layers. So that is called the image definition, where you have numbers arranged in the form of rows and column. And when you talk about digital image processing, we are trying to manipulate, we are trying to change these numbers with some operations, and that is the meaning of digital image processing. Further, we can see the image with through feature space, where you can see physically there are 3 axes: x axis, y axis, and z axis. And here if you take on each axis one band, and then you can plot each band, and where you get the feature vector. So this dot is basically feature vector which is plotted in feature space. So this vector has basically direction, and it has mode of the vector. So 2 things you can get, and by that you can plot the vector in the feature space like this. Here you can see this arrow shows the feature vector which is plotted on 2-dimensional feature space. Now coming to separability analysis, it is basically quantitatively select which subset of bands. If you have 10 bands, out of 10 you may have suppose 6 bands, and that means out of 10, 6 bands are enough to map the given number of classes from the image. So here quantitatively we can select which subset of bands provides the greatest degree of statistical separability between different classes. Discrimination, and here we have to use the discrimination technique that allows separation of major land cover categories with a minimum number of error and a minimum number of bands. That means once we are able to find out the subset of bands, then we can apply the discrimination technique to extract the classes with a minimum number of error and minimum number of bands used in the input image. So if we have training data of each class from each band are normally distributed also, in each band the data is normally distributed. Then we can apply the following methods of separability analysis. The first is transformed divergence, and second is Jeffreys Matsushita distance, and there are two more. One is graphical method, and the fourth one is Euclidean distance method can be used for separability analysis. So here you can see the example of one is graphical method. So graphically, on the three axis you can plot the band values on each band on the each axis, and then you can find out by visually uh, how and which band combination is giving the maximum separation between classes you are going to map. And then if you talk about the statistical method like transform divergence, so in the transform divergence we have to take two parameters. One is mean, and second is covariance matrix from the training data of each class. So here you can see VC and VD is the variance covariance of between class C and D, and MC and MD is the mean parameter of class C and D. And from these you can find out the divergence parameter, and divergence you can use here to get the transformed divergence. So by this formula you can see here you can get the transformed divergence. And if you see the values, the range of values of transform divergence, if the value is 2000 then it is excellent. If the value is above 1900 it is good separation, and if the value of transform divergence is below 1700 then you will get the poor separation between classes. Then second variable what I mentioned is the Jeffreys Matsushita distance. So data should be Gaussian in nature. So here also it requires that the data is following the Gaussian in nature. Removal of least effective features should be there, and transform the pixel vector into a new set of coordinates in which least effective were removed. So overall, if you are seeing the effect of separability analysis, if you have 10 bands, it can remove 4 bands, and these 4 bands are having the very high spectral correlation with the other bands. That's why these redundant bands has been removed, and the minimum optimum bands are kept for mapping the classes you are looking for. So if you apply the Jeffreys Matsushita distance, here you have to calculate the Bhatt variable, again using the mean and variance covariance of two classes at a time. And once you use this Bhatt parameter in this formula, then you can get the Jeffreys Matsushita distance between C and D class. So overall, if you have 6 classes, you have to see permutation combinations and the classes which are giving minimum separation. So that minimum separation should be maximized while using the different band combinations. Like you can start with band 1, then 2 band combinations, then 3 band combinations, then 4 band combinations. If you have up to 10 bands in the image, you can go up to 10 bands and then find out which band combination is giving the maximum separation, and that bands should be considered for mapping the given number of classes. Then coming to digital image classification, the objective of these operations is to replace visual analysis of the image data with quantitative techniques for automating the identification of features in a scene. That means previously there were hard copy images on a paper print, and on that people are doing the visual interpretation, and they were mapping the forest boundary, water boundary, built up boundary, like that. So they were extracting these classes. But today if you have large number of images, it is very time consuming. Of course, through visual interpretation and through visual tracing the accuracy is very high, but it is very time consuming. So people were thought how to cut down the time, so they developed the digital image classification techniques. Through here quantitative techniques, they can automatically classify the pixels in different classes. So here you can see one example of a 5 band image, and you can see image is basically arrangement of numbers in the form of rows and column, and there are 5 bands. So you can apply supervised and unsupervised any classification approach. Overall you see the output is coming as a one layer, and each pixel is labeled to one class. Suppose here all these cyan color is labeled to class 1, that is water. 2 is labeled as vegetation, and 3 is labeled as wetland, and 4 is labeled as soil. Coming to very conventional classifiers, it can be, they have very subcategories labeled to them. One is, they are also called pixel based classifier. Why they are called pixel based classifiers? Because they are using the digital numbers, or we can say they are using the color information, and that's why they are called pixel based classifier. They are using the pixel value of from the image, and that's why these classifiers are called as pixel based classifiers. Same, these classifiers are also called as statistical classifiers, because they are using the statistical parameters like mean, variance, covariance, minimum, maximum, standard deviation, and so forth. They are also called parametric classifier. That means you apply the same algorithm on different data sets for different area. You may found the performance of these algorithms are same, so their performance will not change if you're changing the data and the study area. Plus, these classifiers here I'm talking about as a hard classifier. Hard classifier means either the class is present in a pixel, or the class is not present in a pixel. So you get answer true or false, or yes or no, or 0 and 1. So coming to these, there are two sub classifications we can have in the classification. One is unsupervised classification. That means there is some algorithms you can use them for unsupervised approach. Very basic and simple algorithm is called C means or K means, because this algorithm uses the very simple parameter, and that is the mean of the training samples, so which is a very simple parameter to estimate, and that's why the C means algorithm was developed initially for as to be used as unsupervised classification. Unsupervised classification means we are not providing any label data to the algorithm, and the algorithm is assuming the value of the mean parameter for each class, and that mean parameter is defined with respect to number of iterations. Okay, so that way the algorithm works, and the algorithm iteration will stop if it reaches to the maximum number of iterations to be defined, or the mean shift of the clusters. Each cluster will have its center, and that mean center is shifting at every iteration. And if we find out the mean shift of all the clusters, and that mean shift should be smaller or equal to the threshold cluster center value defined by the user, and if it is true, again the algorithm will stop for further iterating and fine tuning the mean value. So with two parameters we can basically control the algorithm to stop the iteration process. And the second category of classification is basically supervised classification algorithms. Here we are providing the training data or ground truth data to train the algorithm. What do you mean by train the algorithm? We are initializing the parameters of the algorithm. The parameters can be mean, the parameter can be variance covariance matrix elements, the parameters can be minimum and maximum value in each band of the class for the class, and so forth, maybe the standard deviation. So these parameters, as per the requirement, if these parameters are coming in the algorithm, we can initialize these parameters through training data, and then it is called supervised classification. So you can see large number of algorithms developed in supervised classification algorithm. The first one is minimum distance classification, second is Mahalanobis classifier, third is parallelopiped or box classifier, and fourth is maximum likelihood classifier. Since it is supervised, each and every parameter required in the algorithm can be initialized using training data, and that's why here you see large number of algorithms are used. The parameters can be very simple or parameter can be very complex. Any parameter which is there in the algorithm can be initialized using training data, because we are going for supervised classification method. But in the case of, please remember, in the case of unsupervised, the parameter is should be very simple, which can be assumed initially, and the value can be refined, because we are assuming the value and the assumptions are not always true in the life. And that's why we have to further refine the assumed mean value. So that's why you can see in unsupervised you have hardly one algorithm developed as C means, but same C means I will talk in the coming slides. We can use it for supervised also if we are providing the training data. Then in the last you will see I will be talking about, not today, tomorrow again I have one more lecture. I'll be talking about classification accuracy. Whatever output we generate, we have to assess the accuracy. The question comes, what is the application of digital image classification? The initial application was to generate the thematic map from the remote sensing images. That means you want to generate forest area, you want to generate the water bodies area, you want to map the built up area, you want to map the agricultural land with crop, without crop, the waste barren lands and so forth. So these different classes, if you want to map and generate the thematic map, you have to go for classification approach, and nowadays people are going for digital image classification. So here you can see one example of digital image classification, and the example I have taken as unsupervised. So here you can see the input image, what is taken as a 3-band image, and unsupervised classification has been applied. So what the output we are getting, it is a clustered image. That means there is a clusters here, cluster 1, cluster 2, cluster 3, cluster 4, and clusters means here the labels are missing. Labels of missing means we do not know here the blue color is water body or forest. It is just given by default value. The blue color can be C1, cluster 1, and the red color polygon is C2. So that way the numbering is given, or sometimes the algorithm in the software it can be class 1, class 2, class 3. So here you can see one thing is the label is missing in the output. And why the label is missing? Because there was no training data provided. And if the training data is provided, the label comes from the training data. So that is one of the difference when we talk about unsupervised classification. The output is the clustered output. So here you will see the all clusters, not the classes. Please remember, in unsupervised we have to use the word clustering. Clustering means it is unsupervised classification approach, and the output basically it has the clusters where the labels are missing. So how the algorithm works, little bit I can try to draw. And if you have suppose 2-band image, so you can plot the band 1 on x-axis, on band 2 on y-axis. Okay, now since you are going unsupervised, so you can decide a number of clusters. Suppose C is equal to 2. That means you have to assume the mean of cluster 1, or you can write C1, and you have to assume the mean of C2, right? So here you can assume, and here the mean will be 2-dimensional because your image is 2-dimensional. You will have two values here. Suppose here you assume 21 and then 100, and here you can assume it is 50, and then maybe 150 you can assume, right? So here these two cluster centers you have assumed, and then you can start the algorithm. So here algorithm basically is equilibrium distance, and you know the equilibrium distance formula. If you say d I ith pixel, and you can say jth class, so d will be mod of unknown pixel, that is xi minus xj bar. So this is the equilibrium distance equation, where xi is the unknown pixel and xj bar is the mean of the cluster. So mean we have assumed for cluster 1 and cluster 2. So if we use this one, so for first pixel, that is xi, I will be 1. So for first pixel we will get two distances, d1 first pixel first cluster, and d1 first pixel second cluster. So if you compare the distance of both the values for first cluster and second cluster, whichever is minimum, if it is minimum for first cluster, that pixel will be labeled to cluster 1. So like that, you can go on doing labeling for each and every pixel in the image with respect to the minimum distance criteria. And once we get the pixels in cluster 1 and cluster 2, so whatever pixels you got in cluster 1, you use their original image values from the raw input image and find out the new mean cluster for first cluster. Same way, whatever pixels you got in cluster 2, for them you transfer their geolocations on input image and pick out their input values as a two-dimensional values, because the image is two bands, and find out the mean of the cluster 2. So now you have new mean cluster of cluster 1 and cluster 2. So that means initially, if you see, the mean was here for cluster 1, and now the mean is coming somewhere here. So you can see there is a shift of cluster 1. Same way for cluster 2, maybe the cluster 2 was here, it was assumed, and then it came the value here. So it is shifting. So this shift, if you find out its mean value, and then you can compare this mean shift with the threshold value by the user. If it is less than the threshold value, algorithm will stop. If it is more than the threshold value, algorithm will not stop, and then it will check the number of iterations. So if we have defined the 10 iterations and we are at the second iteration, algorithm will go, because iteration is not true and the mean cluster center value is also not true. So in that case, it will go for second iteration using the second mean values which is calculated. Again, it will give the labeling for cluster 1 and for cluster 2 for the input pixels. So again with the minimum distance criteria, some pixels will come in cluster 1 and some pixels will come in cluster 2. So using these pixel value positions, again you calculate the new mean value for cluster 1 and cluster 2. So like this, you will get the new mean value, and these new mean values, again you can use it for classifying the pixels while checking the condition of the number of iteration condition is false, and your the cluster center mean shift is also false condition. So if it is both are false condition, algorithm will go for third iteration, and like that it will go on doing iterations and refining the mean value. Once the condition is true, that is your number of iterations or the mean shift value, if it is true, so algorithm will stop, and then some pixels will be labeled to cluster 1 and some pixels will be labeled to cluster 2. So like that the unsupervised algorithm works, and mainly you can see for unsupervised it is a k-mean algorithm which is using the equilibrium distance. So that means if you have the cluster center here, it will make a circle. So whatever pixels come in that circle are labeled to cluster 1, and whatever pixels come in this circle will be labeled to cluster 2. So that way the labeling is done. Second, coming to supervised image classification. So here you can see the concept of supervised, because supervised means you are providing the training data. So that means you have the label for class 1 A as an agriculture, you have samples for B, that is class is agriculture, sorry, for A is water, for B is agriculture, and for C is rock. So you are taking few samples for each class, that is A, that is B, and that is C, right? So here you have basically 3 band input image, and on that you are applying the samples A, B, and C. And once you apply the supervised algorithm, you get the output, and in the output you can see there are labels, label A, label B, and label C. Okay, so that way this is a supervised algorithm, and in the output you can see for each cluster, the each class, the label is there. We will not use the word here clustering. Here for supervised classification means it is classification, and in the output you see the labels, and because the labels are coming from the training data. So the algorithms, if you see for supervised classification, there are 4 algorithms as a conventional algorithm used. The first one is minimum distance classification, second is Mahalanobis classifier, third is parallelepiped classifier, and fourth is maximum likelihood classifier. So how the minimum distance classifier works? In the minimum distance classifier, the formula is same which I told for unsupervised, that is D I J is equal to mod I can't write because I think pen is jumping here. Use the eraser. So here it is equal to mod of xi, that is input pixel, minus mod of oh, oh, xj bar. So here this is your equivalent distance. Now in the supervised case, this is a unknown pixel xi. It is starting with first pixel in the image. It is going to all the pixels of the image, and xj bar is the mean of a particular class. It can be for water body, it can be for agriculture, because we know we have the ground truth. So we can say the label that means x bar 1 belongs to mean belongs to class water, x bar 2 belongs to class agriculture, like that. So label is there. So once you check the distance for all the classes for pixel 1, and then you find out for which class the distance is minimum, that first pixel will be labeled to that class. So every time you check the distance is minimum for which class, and accordingly you can label that pixel to that class if the distance is minimum for that class. Again, it works for the minimum distance criteria. Second method is called Mahalanobis classifier. In the Mahalanobis, you will see the formula for distance is little different. The Mahalanobis is basically Bengali name. He was a professor at Indian Statistical Institute, Calcutta. So he has proposed this distance. So if you are finding out distance between I and jth pixels, so here you can see the formula for Mahalanobis distance. It is basically bracket xi minus xj bar and having the transpose of it, and then multiplying with A inverse matrix, which is a weight matrix, and again you have xi minus xj bar. So here A inverse basically is a weight matrix. It has three norms. The first norm is unit matrix. The second norm is variance covariance matrix. The third norm is diagonal variance covariance matrix. Oh. So if you are using Euclidean matrix as A inverse, this distance will be working as Euclidean distance. If you are working A inverse as variance covariance matrix, then it will be working as a Mahalanobis distance, because you are using the variance covariance elements. And third special case is if you are using diagonal variance covariance matrix as A inverse, again it is a special case of Mahalanobis distance. In your 12th class or in the 11th class, you have learned about Euclidean distance. So Euclidean distance is this one, which I have already drawn here, written here. But the general distance equation is this one and this one. And as per the A inverse you are taking, it is unit matrix, or it is variance covariance matrix, or it is diagonal variance covariance matrix. Accordingly, you can have the Euclidean distance or Mahalanobis distance. So once you are working with Mahalanobis distance classifier, here also we have to find out the minimum distance between the unknown pixel, that is xi, and the mean of particular class. And here you can see it is using variance covariance matrix. So the variance covariance matrix is a very complex variable. It cannot be assumed or refined in the case of unsupervised. That's why Mahalanobis distance has never been used for unsupervised, because this variable A inverse cannot be refined, and that's why this is used always as supervised algorithm case. So if you are using again I'm telling variance covariance matrix form of A inverse or diagonal variance covariance matrix, then it will work as Mahalanobis distance with two types. And then again, if the distance is minimum, and accordingly you can label to the particular input pixel to your class 1, class 2 or class 3. If you are extracting 3 classes, that means class 1 is water, class 2 is your agriculture, and class 3 is your forest. So you can get the mean of each class, that is water, agriculture and forest, as well as you can calculate the its variance covariance matrix, and both you can use in this distance, and then you can find out distance of first pixel with water, distance of first pixel with agriculture, and distance of first pixel with forest, and whichever it is minimum you can label that pixel to that class, then take the second pixel and again find out distance with water, and distance with agriculture and distance with forest, and whichever is minimum you can again label. So that way you can do the labeling, and in single iteration you can finish the Mahalanobis supervised algorithm approach. The third I have listed here is parallelopiped classifier. This is also called box classifier. So by the name itself, if you have training data of suppose water, if you have first sample, second sample and so forth, suppose 10 samples you have taken, and if it is two band image, that means you have sample from band 1 for water and you have sample for band 2 for water. Then from these training sample of water you can find out two type of variables. One is like mean of water, plus you can also find out the standard deviation from this training data for water, standard deviation right, for band 1 and band 2. And then if you want you can go for second type of variable, that is minimum and maximum on band 1, same way minimum and maximum at band 2. So once you have these variables, you can draw the feature space B1 and B2. If you are taking mean on band 1, then you can draw the standard deviation minus and standard deviation plus. Same way mean on band 2, then you can take standard deviation minus and standard deviation plus. And if you extend these values in this graph, you can create a box. So you got a box here. So this box represent to class water because the training data belongs to class water. So whatever pixels are there in this box will be labeled to class water. Same way you can create the box for agriculture, and whatever pixels comes in agriculture you can label that pixels to agriculture. Second mode, if you want to work on the same data of two bands, band 1 and band 2, you can take the variables minimum maximum on band 1. So this is minimum and this is maximum. Same way on the band 2 for class water, this is minimum and this is maximum. Now if you join these points, again you can recreate the box, right? You can recreate the box. So whatever pixels are there in this box, you can label to class water. Same way you can create the box with minimum and maximum parameter for agriculture, for forest. So whatever pixels come in that box, you can label to class to forest and agriculture. But there can be issue here and other algorithms. Here you may found the two boxes are overlapping to some certain extent. So here it is overlapping. So you have to make your own rules. Algorithm does not tell any solution for that. If there is overlap, you can divide this overlap area 50-50 and divide that 50-50 to both the classes, or this area you can just discard and say it is unclassified pixels. So that way you can provide the solutions, because these practical issues you will encounter when you are using these conventional algorithms. The fourth algorithm is called maximum likelihood classifier, right? So in short it is called MLC, maximum likelihood classifier. And in this formula it works on probability criteria. So you have to generate the probability parameter P 1 upon 2 pi to the power n by 2, and then mode of A inverse weight matrix, which I told previously also. You have to get its mod, and then e to the power minus 0.5 bracket xi minus xj bar transpose of this vector difference, and then A inverse xi minus xj bar. So here you are getting the probability formula. The variables, you can say this is 2 pi, you know, n is number of bands, A inverse is a weight matrix, it has 3 norms. It can be unit matrix, it can be variance covariance matrix, and it can be diagonal variance covariance matrix. Xi is the input pixel, xj bar is the mean of the class. So if you put all these variables for class water, so you can find out P1 for water. Then again, if you are getting agriculture, you can get P1 for agriculture. Then P again for first pixel for class forest. So you got probability of 3 classes for water, agriculture, and forest for class 1, and whichever the probability is maximum. Here, please remember, we are finding we are finding out and we are calculating the probability of each pixel belonging to particular class. So whichever it is maximum for a particular class, that the label will be given to that class. If the probability of water is maximum for first pixel, so first pixel will be labeled to class water. So this way the maximum likelihood classifier. But these algorithms, once they are using variance covariance matrix, these algorithms has to follow the normal distribution. If your training data is following the normal distribution like this, then these algorithms will give you the very good results. In case your data in each band, you can check on the training data, they are not following the normal distribution. So the algorithms which are using variance covariance matrix, like one is probability maximum likelihood classifier, if it is using A inverse as a variance covariance or diagonal variance covariance matrix, or Mahalanobis distance, if it is again using the variance covariance matrix. So these algorithms may not able to give the very good results if the data is not normal distribution. On the commercial point of view, if you see the commercial softwares, they are using only the variance covariance matrix in the maximum likelihood classifier. But research point of view, you can apply all the 3 norms of weighted matrix. It can be Euclidean norm, that is your unit matrix, or variance covariance matrix, or diagonal variance covariance matrix. Same way for Mahalanobis distance, in the Mahalanobis again you can have 3 norms using unit matrix, using variance covariance matrix, and using diagonal variance covariance matrix. So if you are using unit matrix or identity matrix, the Mahalanobis classifier will work as a minimum distance Euclidean distance classifier. So that way these algorithms works, but very special case has been applied in the commercial tool. But if you are developing your own small program, writing your own program, so you can test with all the 3 norms of weighted matrix. The weight matrix, you can use it as a Euclidean distance, or variance covariance distance, or diagonal variance covariance distance. So this is all about my today's lecture. And these classifiers, if you see category wise, I have told you they are coming under 3-4 categories. The categories are basically pixel based classifier. That means these classifiers are using pixel values from the image, and they are using statistical parameters like mean, mode, and your variance covariance, minimum distance parameters, standard deviation. That's why they are also called statistical classifiers. They are having the parametric approach. That means you apply the algorithm for image of one area, or multiple images of same area, or images of different area. Its behavior of the algorithm will remain same. It will not change, and you don't have to change the parameter of the variables for the different images. So that's why these algorithms are also called as a parametric classifiers, and these algorithms are also called hard classifiers. Okay, Hard means they are telling in 1 pixel there is water or there is no water, right? So it is saying the answer is yes or no, true or false, like that, or 0 and 1. So this is all about today's lecture. I started talking about what is image, and because that is understood, you have to understood in the mathematical form, the numbers are arranged in the form of rows and column, and you can have single layer if it is panchromatic image, or it can be multiple layers if it is like multispectral image, and more layers as a band you can see if it is hyperspectral image. Generally for these conventional classifiers, the panchromatic image is not used because they are pixel based classifier. They are using pixel values from the image, so that should be two or more than two bands. So then I talked about the separability analysis. The separability analysis is a method developed to know the minimum number of or optimum number of bands which having the least spectral overlap. That means each band is giving very unique information, and with that we can have a subset of spectral bands from a given image, and we can map very nicely the given number of classes from the optimized subset image. There are four methods I've listed out for separability analysis. The first is graphical method I talked about. Second is your Euclidean distance, and third is your Jeffrey-Matsushita distance and transform divergence. These methods you can see very nicely. You can read more in detail if you want. You can go for Jensen Introductory to Digital Image Classification book. So there, with the example of Landsat images, Jensen author has explained the separability analysis very nicely. Then I went to the what is image classification and what is digital image classification, and the subclasses of your classification approach. There are two branches has been developed. First one is unsupervised classification approach, where training data is not used. And one more thing I would like to mention for unsupervised classification, one unsupervised algorithm. The unsupervised algorithm is applied where we don't have training data obviously, but what is the application of unsupervised classification? If you have an image of particular area and you do not know how many number of classes are there to be mapped, so what you can do, you can apply unsupervised classification approach, and you can take number of clusters to be 50, and then you will get 50 clusters. And then if you have little some basic very preliminary information about the study area, if you have your own experience the way the classes should appear on the remote sensing images, then you may found that some of the clusters are belonging to more or less same class. So you can merge these clusters, and that way in place of 50 clusters you may get hardly 30 clusters in the output image, and this will tell you the answer that from a given image, and if the image belongs to a particular area but you do not have the study area, you don't have the ground truth or training data information. So the unsupervised algorithm tells you from this image for a given area how many number of classes you can map. Then coming to supervised classification, as I mentioned, you require training data or prior knowledge for training the algorithm. Training the algorithm means you are generating mean, you are generating you are initializing the statistical parameters used in the algorithm. It can be mean parameter, it can be variance covariance parameter, it can be minimum and maximum parameter, it can be standard deviation, and so forth. That is initialized by the training data, which is collected from the ground truth or by any reference data. And then broadly, if you see the very basic conventional algorithms, which is there are four. One is minimum distance algorithm, second is Mahalanobis classifier, third is parallelopiped or box classifier, and fourth is maximum likelihood classifier. Out of these four algorithms, if they are using the variance covariance matrix parameter, then these algorithms will require that your data follows the normal distribution concept on each band. Otherwise, these algorithms which are using variance covariance matrix will not give you the good results. Tomorrow, I will talk about the classification accuracy. That means using these algorithms, we have generated the thematic map. And the question is, what is the accuracy of this thematic map? So for that, we have to apply the classification accuracy method, and the method developed is called your error matrix or confusion matrix. So tomorrow we will learn about confusion or error matrix. Thank you all for attending today's lecture of basics of remote sensing GIS DIP part of EduShare.